Hello, welcome to section 10.9, Convergence of Taylor series. This is the last section in chapter 10, which means after this section, we're done talking about series. We're going to move on. So previously we looked at how to find a Taylor series and how to find a Taylor polynomial and the Maclaurin series and the Maclaurin polynomials. And the question now is going to be, when do these Taylor series converge? And we saw some examples of actually sitting down and finding out when it converges, but we're going to try to find an easier way to determine when these Taylor series converge. And we're also going to look at how well does a Taylor polynomial approximate the function. So to do this, we start with Taylor's theorem. Taylor's theorem says that if f and its first n derivatives are continuous on the closed interval a to b, and if the n plus first derivative of f exists, it does not have to be continuous, it just needs to exist on the open interval a to b, then there is a number c sandwiched between a and b such that the function evaluated at b is equal to f of a plus the first derivative of f evaluated at a times b minus a plus the second derivative divided by 2 factorial times b minus a squared plus ... come down here, plus the nth derivative of f evaluated at a divided by n factorial times b minus a to the n plus the n plus first derivative evaluated at c divided by n plus 1 factorial times b minus a to the n plus 1, period. So what is this saying? This is saying that there exists some c such that you can evaluate f at b, and this Taylor series is centered at a. So evaluate f at b, and you get a Taylor polynomial plus this extra term. And notice we have straight equality, not approximately. So we're saying that while the Taylor series, the truncated Taylor series, so a Taylor polynomial, is a good approximation of the function, we're saying that no, it just straight equals it if you can find this value c. And notice this kind of looks like the mean value theorem. The mean value theorem also had this, there exists a c between this interval such that the derivative exists. So how did Taylor envision using this? We have Taylor's formula. If f has derivatives of all orders, in an open interval I, and this open interval needs to contain a. So again, think radius interval of convergence. And then for each positive integer n, and for each x in this interval of convergence, we have f of x equals f of a plus the first derivative of a evaluated at x minus a plus ... We have the nth Taylor polynomial plus that extra term that involves c. and this is true for some c between a and x. So he said, well, it's not only true for f of b, it's true for every x in this interval of convergence. And let me move this down. I want more space. And so what we're going to do is we're going to look at the first n terms. This is Pn of x, the Taylor polynomial. And then this last term is going to be labeled Rn of x, which we will call the error term. And this is actually really great because if we can show that this error term goes to 0 as n goes to infinity, then we can say that the Taylor series of f of x converges to f of x on I. So and we never actually define convergence for a Taylor series, so we'll say that this is what we mean by converges, that to f of x on I. So to say it converges means that we can say that f of x equals this Taylor series. This is excellent. So all we have to really do is show that this error term is going to go to 0. But there's a problem with Taylor's formula. If you look back up at Taylor's formula, and this is also true for Taylor's theorem, it just says that there exists some c. It doesn't ever tell you how you're going to find this c. And you need the c in order to show that Rn of x goes to 0. So unfortunately, we can't just do this for every function. We have to have certain requirements met for the function in order to show that Rn of x goes to 0. So let's do an example to see one such function, and then we'll go into more detail about how we can approximate this error term. So show that the Taylor series of f of x equals e to the x at x equals 0 converges to f of x for every x. So we could use the ratio test. Set up the ratio, take the limit, see that hopefully the limit will go to 0 no matter what x we pick. Or we can use Taylor's formula. So to use Taylor's formula, you would say f of x has derivatives of all order. On the open interval negative infinity to infinity, so over the whole real line. So we have, by Taylor's theorem, not theorem, sorry, formula. And we're using the Taylor series of e to the x, which we found in the last example of the last section. So we would have e to the x equals 1 plus x squared over 2 plus plus x to the n over n factorial, the Taylor polynomial, plus e to the c for some c divided by n plus 1 factorial x to the n plus 1. This is true for some c between 0 and x. And again, we're calling this the error term, Rn of x. So we consider three cases. First, what happens if x is greater than 0? If x is greater than 0, then c has to also be greater than 0. It's sandwiched between 0 and x. Raise everything to do e to the power of everything, and you get 1, which equals e to the 0, is less than e to the c, is less than e to the x. So, the absolute value of Rn of x equals the absolute value of e to the c, x to the n plus 1, divided by n plus 1 factorial. We have too many variables here to be taking a limit as n goes to infinity because we have this c. But we can say that e to the c is less than e to the x. And now we know that x is some fixed value. We will fix x. And so as x is fixed, as n goes to infinity, the denominator is going to win. The factorial is going to grow faster than some constant to the n. So this is going to approach 0 as n goes to infinity, which is what we wanted. We have shown that the error term goes to 0, so therefore this function converges to the Taylor series for x greater than 0. We now do the case that x equals 0. If x equals 0, then we have 0 is less than c is less than 0. So c has to equal 0. So Rn of x equals e to the 0 times 0 to the n plus 1 over n plus 1 factorial equals 0. So it also goes to 0. So R for all, forgot my variable. This is true for all n bigger than or equal to 0. So the error term went to 0, so we're good. And the third case, we have x is less than 0. Then, since c is between 0 and x is less than 0, we have x is less than c is less than 0. And do e to the power of all of these, and you get e to the x is less than e to the c is less than e to the 0, which equals 1. So the absolute value of this error term is, again, e to the c, x to the n plus 1 over n plus 1 factorial, which is less than the absolute value of x to the n plus 1 over n plus 1 factorial, which again goes to 0 as n goes to infinity. So since Rn of x goes to 0 for all x, we have e to the x equals the summation from n equals 0 to infinity of x to the n divided by n factorial. And fun fact, if you evaluate this function at 1, then you have a nice way to approximate e. And you can just keep adding more terms. You approximate it with the Taylor polynomials. If you just keep adding more terms, you get a better approximation. So as was shown with this example, we have to do approximations in order to show that Rn of x goes to 0. So this leads to the remainder theorem estimator, a remainder estimation theorem. Had the words backwards. So the remainder estimation theorem gives us a way to approximate this Rn of x more easily than having to break it up into 3 cases and going from there. So if there is a positive constant m such that the absolute value of the n plus first derivative of t is less than or equal to m for all t between a and x inclusive, then the remainder, which we labeled Rn of x, in Taylor's formula, satisfies the inequality. The absolute value of Rn of x is less than or equal to m times the absolute value of x minus a to the n plus 1 divided by n plus 1 factorial. So, example, let's use this to show that it is easier to use this than the previous example, breaking it up into 3 cases. Show that the Taylor series of f of x equals sine x converges to f of x. So solution, to do that, all we have to do is show that this error term goes to 0. So we're going to bound it above by this function, and then we're going to show that this goes to 0. So first off, recall the Taylor series of sine x. This was the summation from n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1, divided by 2n plus 1 factorial. Key thing to note here is this only has odd powers of x. So we only have to consider odd n. We do not have to do this for in general. It doesn't make sense to consider the 2n Taylor polynomial because that is equal to the 2n minus 1 Taylor polynomial because the coefficient of x to the 2n is just going to be 0. So since for all n, if you take the 2n plus first derivative of f of x, this is equal to the absolute value of cosine x, and this is less than or equal to 1, versus if you take the even-powered derivative, this is going to be equal to the absolute value of sine x, which is also going to be less than or equal to 1. So, in other words, we can bound the n plus first derivative of f of x by 1. So we let m equal 1. So the absolute value of r sub 2n plus 1 of x is less than or equal to m, which is 1, absolute value of x minus a. In this case, we're doing the Maclaurin series, so the absolute value of x, to the 1 more than the remainder that we're looking at, so 2n plus 2, divided by also 2n plus 2 factorial. And this goes to 0 as n goes to infinity. So sine x equals the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1, over 2n plus 1 factorial. In other words, this power series converges to sine x. Okay, 2 more examples we're going to move away from showing that the Taylor series converge, because as you see, this isn't too hard to do. You just take derivatives and then bound them, and oftentimes you'll get a constant, and then the factorial is going to grow so much larger than other things that this is almost always going to go to 0. So since Taylor series are just power series, all the operations that we did on power series, we can do on Taylor series. And we saw a few examples of this in the last section. I'm just going to do one more to show that, look, you can do this with, say, sine x, cosine x, e to the x. You can do that with, do this with all those functions that we have shown converge to have a power series that converges to it. So example, find the first few terms of the Taylor series of 1/3 times 2x plus x cosine x. So we have 1/3 times 2x plus x cosine x is 2/3 x plus x over 3 times the Taylor series for cosine x. Recall the Taylor series from cosine x was the sum from n equals 0 to infinity of -1 to the n x to the 2n over 2n factorial. Same as the Taylor series for sine x, but you take all even powers instead of odd powers. Okay, distribute this x here, and you get 2/3 x plus 1/3 sum from n equals 0 to infinity of -1 to the n, x to the 2n plus 1 over 2n factorial. Write out the first few terms. You get 2/3 x plus 1/3 times, when n equals 0, you get a positive 1. You get a 1 factorial in the denominator. When n equals 0, you just get x to the first. When n equals 1, you get -1. You're going to get x cubed. You're going to get all odd powers now of x divided by 2 factorial. So that's minus x cubed divided by 2. It oscillates, so we'll do plus. When n equals 2, you get x to the 5th divided by 4 factorial. And we'll just keep so on and so forth. All right, distribute the 1/3. You have 1/3 x plus 2/3 x. So that is x minus x cubed over 6 plus x to the 5th divided by 4 factorial is 24 times 3 is 72. And these are the first few terms of the series. So everything we did with power series, we can do with Taylor series. We can add power series. So we added, wrong thing, laser pointer. We added the power series of cosine x to the power series of 2x. Luckily, the power series of 2x is very easy. It's just 2x. And then you can multiply by power series. So we just multiplied this x into all of the terms. Nothing too difficult. So last example. We talked about the remainder estimation theorem. And so if we can bound this remainder, that means that we can see how close a Taylor polynomial is to approximating the function. How well does it approximate? So let's see an example of this. For what values of x can we replace sine x, by x minus x cubed over 3 factorial with an error of magnitude no greater than 3 times 10 to the negative fourth. So notice this is x minus x cubed over 3 factorial. These are the first two terms of the power series for sine x. So we're really saying for what values of x does the Taylor polynomial, the degree 3 Taylor polynomial, approximate sine x with order of magnitude with error no greater than 3 times 10 to the negative fourth. So we actually don't need the remainder estimation theorem for this one because we know that the Taylor series for sine x is an alternating series. So the error term is bounded above by the first unused term. So sine x we know is x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus dot dot dot. We are truncating it at x cubed over 3 factorial. So the error is no greater than the absolute value of x to the fifth over 5 factorial. We want the error less than 3 times 10 to the negative fourth. So we're trying to solve the inequality x to the fifth over 120 is less than 3 times 10 to the negative fourth. Multiply by 120, you get the absolute value of x to the fifth is less than 0.036. Take the fifth root, and you get the absolute value of x is less than the fifth root of 0.036, which is approximately 0.514. So the error is no greater than 3 times 10 to the negative fourth if x is between negative 0.514 is less than x is less than 0.514. So as long as x is within basically 1/2 of 0, we know that the order of magnitude will be no greater than 3 times 10 to the negative fourth if we use the first two terms of the Taylor series. Add another term and the error term will get smaller and smaller and smaller. So you'll be able to expand this interval if you add